correctly, and as per theoretical calculation we have designed the antenna, and the antenna is not working properly. Antenna is not resonating at the design frequency. It is resonating at a lower frequency. And now you know what is frequency. Frequency is equal to C by lambda, and antenna length is half wavelength. So C by lambda by 2, that is the length. C by lambda by 2, that should be the frequency. Now the frequency is lower, means lambda is larger. So we have got a larger length. Ultimately we have got a larger length. What is the reason for this larger length? Because of the larger length we are getting all the problems. So what is the reason for the larger length? Let us investigate that. As I told you earlier, when we discussed about dipole antennas, or when we started discussing about antenna, the dipole antenna we can consider as two parallel wire transmission lines. So one transmission line with two parallel wires. Now, and at the end of the transmission line, it is open circuited. It is not terminating on any load, so it is open circuited. And from the end, we have folded the transmission line in such a manner that the length of the folded portion is lambda by 2, half wavelength. Length of the folded portion is lambda by 2. Now there will be two arms. Each arm will be lambda by 4. Total length is lambda by 2, so each arm will be lambda by 4. If we do not fold it, assume that we have not folded it initial stage. If we do not fold it, then this folded portion, and we consider only the folded portion as transmission line, it will be a lambda by 4 transmission line. Now look at the transmission line. The electric fields come from positive end to negative end because it is open circuited. At the end, the electric field will terminate it. So exactly at the physical end, electric field will be terminated. We have assumed that this is what is happening, but in practice this is not what the case is. The electric field at the end or at the edge, they will fringe out. So because there are other paths from the edge, there is a path from the edge to go from the upper edge to the lower edge. So it will fringe out. Although it will be weakened exactly at the physical end, the field strength will be maximum. Then it will fringe out. The field strength will weaken, and at a large distance it will be 0. Okay, next. So there is fringing. So total length is L, physical length is L. Because of the fringing, so electric field will exist substantially for another additional length, which we call delta L. So total length is in this way. Total electrical length is not L, not the physical length, but it is the physical length plus the length due to fringing fields. So it will be L plus delta L. This delta L we have not taken care of when we designed the antenna. Because of this delta L, there will be problems. The problems that we have seen, the frequency is not 920, but it has come down because length is more. So electrical length is more, not lambda by 2. Now it is more than lambda by 2, so the frequency has come down. So now we will come to the other portion. Why there is reactive part? Once it has increased, why there is reactive part? Why frequency has decreased? That we have seen. Why there is reactive part? Next. You know, the input impedance is equal to Zin is equal to Z0 into ZL load impedance plus JZ0 tan KL divided by Z0 plus JZL tan KL. ZL is load impedance, Z0 is characteristics impedance, L is length, K is 2 pi by lambda. Okay. Now for a open circuited line, and Zin is equal to, in this formula, if Zin small Zin is capital Zin by capital Z0. So in this formula, small z in will be minus jz0 cot kl. This we have already seen. So cotangent kl, z in is equal to minus jz0 cotangent kl. Now when n is greater than lambda by 4, this z in will be positive, which means this will give an inductive path. So this will give inductance. This will result in inductance. So this additional length, because of the additional length, we will get the inductance. If it is smaller than lambda by 4, then we will get capacitive. But since it is more than lambda by 4, L plus delta L, L is lambda by 4 plus delta L, so that is more than lambda by 4, that will give us a positive part or a reactive part which is inductive. So therefore, we get an inductive part. In the impedance, we get an inductive part along with the resistive part. So resistive part plus inductive part, now it has changed, so it will not be 73 ohms. So all these things happen. The frequency goes down, then the impedance is not pure resistive, the resistance is not 73. All this happens because of this elongation in length or electrical length is more than lambda by 2. So what is the solution? Next, what is the solution? Solution is, let us decrease the physical length, otherwise everything remains same. Only you can see same 900 band, everything remains same, center frequency 920, wavelength 326.08, diameter 16.3, gap is 8.15, everything remains same. Only the length will change. Dipole length, this is a thumb rule, you can follow this. Instead of taking 0.5 lambda or 0.5 L, L is wavelength. So wavelength lambda, that I am writing as L. So 0.5 L, you take it to be 0.48 L minus d. Why d? The current is not only along the z axis, it is along the diameter also. So that much distance in the current that is to be taken care of. So total distance is 0.48 L minus d. So if we to take that, that will give us 140.2 mm. So once we get this, then the design is easy. As we have done the design, follow the same process. Next. Follow the same process, only here you change H to be, H was 0.5 L, now H is changed to be 0.48 star L minus D. That was changing the H. Other parameters are same. So go to the project variables. In the project variable, only change the variable H. H will be 0.48 into L minus D. That much change you make. So then click OK. So next. Now I'll do the simulation. Follow the same procedure, the process that we had followed. Follow the same process. Now do the simulation. You can see the dip is exactly at 920, almost exactly at 920, which means it is now originating at the desired frequency. So what frequency we desired, at that frequency it is originating. Then look at the bandwidth. Bandwidth is, when you see this, should look for minus 10 dB. So in the y-axis, look for minus 10 dB. Draw a line along minus 10 dB. That will meet this curve at around 800 on the left hand side and at around 1.1 or 2, no sorry 1.1 or less than 1.1, more than 1.05 or 06, somewhere there. So 0.8 to 1.06, that is the bandwidth. If you draw a horizontal line at minus 10, you can see here it will be from about from about 800 megahertz to 105 1.05 gigahertz. Up to that much frequency we have got. So that covers our required band. Okay, next. So you can see the bandwidth. Then what we can do is we can go click on add marker. Then we can put the markers. Once you click on add marker, put the markers. One marker at this point. So 3 markers I have put. One at the deep, one at the left point where the core meets the -10 dB line, and one on the right hand side where the core meets the -10 dB line. So these points are the first marker, which is on the left side, is at 0.8070. The peak is, the deep is at 1.06. The deep is M3 is at 9110, which is about 120. So we have come to about 120. Right hand side M2 is 1.06. So complete thing is covered, and we have got it at the required point, almost at the required point. Then we do the other analysis. So now instead of S parameter in this analysis, so go to the setup. In the setup, instead of S parameter, now take the Z parameter. In the Z parameter, we look at imaginary and real part. So click on imaginary and real. In the function, under the function, click on imaginary and real. These two you have to select. Click them, they will be blue. Now you can see the imaginary part and real part, and put the markers at the points where the our imaginary part is 0. Corresponding to that frequency, look at what is the red one is for resistance. So on the resistance corresponding to the frequency where M1 is there, put M2. So those frequencies are 912 or 911, so around that, 910 to 20, somewhere there. So both are the frequencies that I require, and the red curve gives us 73.94. So 73 ohms that we require for the dipole, that also we are getting here. The reactive part is very small, 0.15, so that can be neglected. Okay. So on the required part we have got for the antenna, designed antenna. Then do a Smith chart plot. How to do the Smith chart plot, that I am showing here. And go to the antenna on the left hand side, optometrics, below the optometrics, go to this results, right click on the result, you will get this, the window, first window. Under the page there is create model solution data report. Then on the data report you will get another window. On that window click on Smith chart. So once you click on Smith chart, what you are going to plot on the Smith chart is the S parameter. So click on S parameter and click new report, generate new report. Next. So once you do that, you will see this curve. This curve shows you that the antenna is resonating at M3, marker M3. That is the point where it is resonating. Now for M3 you can see what is the frequency, 911 megahertz. Then what is the impedance? It is 1.0083 minus 0.009. So it is 1, approximately 1. On this Smith chart is a normalized chart. Therefore it is 1 means it is 73 ohms. Don't confuse it. So whatever is coming, 1.0083, that into 73. So that gives you approximately 73 ohms. So at the center you are matching it. So it is properly matched. So M3 is properly matched. It is at the required frequency, 9110, almost at the required frequency. Then starting frequency, ending frequency, they don't matter much. And you can see that this antenna is mostly inductive. A dipole antenna is mostly inductive. So around that part you can see from M3 to, as you move towards M3, M2, it is mostly inductive, and it is within the bandwidth if you draw to VSWR is equal to 2 circle, then a large portion of this bar will be within the VSWR 2 circle, which means it is having a large bandwidth. Next. Then we have to see the radiation pattern, radiation fields of this antenna. So to do that, on the main window, project manager window, go to radiation, right click on the radiation, then go to insert far field setup. You can do the near field setup, but I want to see the radiation pattern, so we are going to going for the far field setup. So insert far field setup, then in that far field setup, click infinite sphere. So then once you click that, how to construct the sphere? Sphere is constructed by theta phi. Phi is minus 180 to 180. Step size, let us take 1 here. Then theta is 0 to 180. Step size again, let us take as 1 here. So click OK on that. So our name is 3D far field for the antenna. Okay. Then on the P plane, next one is give it where P plane. Then starting phi is equal to 0, stop is 0. You are only in the P plane, means phi plane. For phi plane, I am writing is P plane. So P plane, start 0, stop 0, step size 0. So you are phi is equal to 0. That is on that plane we are considering this. Then theta is minus 180 to 180. Step size is 1. So this is another. Then next. Then this and the second one, P plane 2, second P plane, start is minus 180, stop is 180, step size is 1, theta will take on the 90 degree. So we can give it P plane 2 or T plane. So theta plane. T plane is theta plane. So theta is not changing, theta is at 90 degree. So it is on the XY plane. Theta is equal to 90 degrees. It is on the XY plane. Start 90, stop 90, step size 0. Okay. Then come to this results. In the result, go to create far field report. In the far field report, go to radiation patterns. Click on the radiation patterns. So then in the radiation pattern, what you want to see? Usually you will like to see the gain of the antenna. So click on gain. In the gain, quantity will be total gain. There will be different types of gain. Always to choose the total gain. So gain total, then function in terms of dB. So gain in terms of dB. So dB. So gain total, then dB. Then close it. Then you can see the radiation pattern. So this is the first radiation pattern. You can see the figure of 8 rotated by 90 degree. So this is what the radiation pattern of a dipole antenna. So dipole antenna is around the z-axis, means it is oriented from 0 to minus 180 or minus 180 to 0. Along that the radiation antenna is oriented. Along that you get the dip, which means there is no radiation along the antenna. Perpendicular to the antenna, the maximum radiation is there. So it is a rotated figure of 8. And that pattern we have got, which is matching the theoretical pattern. Go to the next one. So you can double click on this. These values 2, 14, minus 26 are given. So double click on that. Then change this value. Once you click on that, we can change the minimum value, maximum value of the scale. So change values, minimum values, let us make it minus 20. Maximum value is 5. Spacing is 5. So once we do that, then the pattern becomes exactly a figure of 8. Okay, so to get this pattern, you have to make those much changes, minimum value and maximum value. Those changes you can do. You can experiment yourself. You can do the experiment and see what will be the minimum, what will be the maximum, for which you get the proper pattern. Next. And then again go to results. Then right click on results. go to create far field reports, then go to 3D polar plot. So 2D we have seen, now come to 3D polar plots. In the 3D polar plots, solution is set of one, least adaptive, then geometry is 3D far field, that is what we are going to do. Primary sweep will be in the phi, so phi will change. Secondary sweep will be theta, theta will change after that. So first phi will change, then theta will change. That is what it means. Then phi will take default, theta will take default because it is 3D. We are not going to change anything. Then what we are going to do, we are going to look at the category which is directivity of the antenna. Quantity is total directivity. It will be a function in dB. So we will measure it in dB. Now once you click on that, you will see this pattern. The antenna will be along Z direction, and you will see the pattern being like this. So this is the 3D pattern of a dipole antenna, half-wave dipole antenna, 3D pattern that we have designed. Now, if you are not very comfortable with that pattern, because everything seems to be red, so let us change it. So click on this, come to the scale. On the scale, click on, make a right click, then modify. If you modify, so then you can see, go to the scale, click on the scale, then next. Change the limit. So instead of auto, go to use limits. So we will go to use limits. Change as required. Here we are changing the limit. Minimum is -20, maximum is 2.5549. So that is the change that we have made. So minimum, maximum we have changed, -20 to 2.55. Apply that. So the scale will change. Once scale will change, this will be more clear. And so the maximum is along the theta is equal to 0, that is clear. Minimum is along, maximum is along theta is equal to 90. Minimum is along theta is equal to 0. And you can see a more clear radiation pattern. Green part shows you that there is no radiation along that. The red part shows you there is radiation, maximum radiation. So green to yellow to red, how the radiation changes as you move from the antenna and the orientation towards the broadside, how the gain changes or directivity changes, that you see through this radiation pattern. Then go to the drop-down list. In the drop-down list, click on the pan. First you click on the pan. Once you click on the pan, main pan, you will get this drop-down list. From the drop-down list, go to plot fields. In the plot fields, then you go to radiation field. Okay. Once you go to radiation field, then click that. Then it will show you 3D directivity. Click this visible. Visible will be not ticked. Now you tick this visible. What does this mean? Which means the antenna is to be visible. We are seeing, up to now, we have seen only the pattern. We didn't saw the antenna. Now the antenna and pattern both will be seen. So once you tick the visible, antenna will be visible. So tick visible, click on apply. Now you can see the antenna as well as the radiation pattern, both. The orientation of the antenna and the radiation pattern, both you can see. Okay. So with that, we come to the end of simulating a dipole antenna in HFSS. I hope you have understood it. You have taken snapshots for designing this antenna. I will be happy if you can design this antenna yourself and tell me if there is any problem. So now, if you have anything to say, tell me. You can please tell me now, otherwise you will stop. ଦେଖିଲା ସିମୁଲେସନ୍ କେମିତି ହୁଏ, step by step କହିଲି.